There are moments in science that never make the headlines they deserve. A small team, working out of a university lab far from any press conference, quietly publishes a paper that ends up rewriting the timeline for one of the most important technologies of this century. I want to walk you through one of those moments, because when you actually dig into what a team at the Pritzker School of Molecular Engineering at the University of Chicago published in Nature Physics back on April 29th, 2024, and then trace what's happened in the 2 years since, you realize almost nobody outside the quantum physics community fully grasped what had just happened. Here's the short version. The single biggest engineering obstacle standing between us and a truly useful quantum computer just found a real, physically credible shortcut. Not a small tweak, not another incremental press release. A genuine change to the math of how many components you need to build a machine that actually works. And as of mid-2026, the ripple effects of that shortcut are now showing up in the roadmaps of IBM, Google, and quantum hardware startups racing to be first through the door it opened. To understand why this matters, you need to understand the problem first, because it's the kind of problem that sounds abstract until you realize how concrete its consequences are. Every computer you've ever used, your laptop, your phone, every server running the internet right now, works with classical bits. A bit is a switch, on or off, 1 or 0, simple and stable. A quantum computer works with qubits, and qubits play by a completely different set of rules. A qubit can exist in superposition, meaning it's effectively both a 1 and a 0 at the same time. Chain enough qubits together through entanglement, where the state of one qubit is tied to another regardless of distance, and you get a machine that can explore millions of possible answers simultaneously instead of checking them one at a time. That difference in approach is why certain problems that would take the fastest supercomputer on Earth longer than the age of the universe to solve could, in theory, be finished by a fault-tolerant quantum computer in minutes. This isn't science fiction potential. It's drug discovery, where modeling how molecules actually interact at the quantum level could compress a pharmaceutical development pipeline that today averages somewhere around 10 to 15 years down to a fraction of that. It's climate modeling with a level of chemical precision classical machines simply can't reach. It's the RSA encryption standard that currently protects nearly every piece of sensitive data moving across the internet, your bank transactions, your messages, military and government communications. That's why the United States, China, and the European Union are all pouring billions into quantum research at the same time. Whoever gets there first doesn't just win bragging rights. They get a strategic and economic advantage nothing else in technology can currently match. But here's the nightmare that has kept most of that potential locked away for 2 decades. Qubits are almost impossibly fragile. Not fragile like glass, fragile in a way that barely has a real-world comparison. Tiny temperature fluctuations, microscopic vibrations, stray electromagnetic interference, even a passing particle near the processor can knock a qubit out of its quantum state and introduce an error. Physicists call this decoherence, and it's the central villain of the entire field. Today's best quantum processors run with a physical qubit error rate around 1 mistake per 1,000 operations. That sounds tolerable until you realize that a genuinely useful quantum algorithm, the kind that could simulate a protein or crack an encryption key, might require not thousands but billions of individual operations. At 1 error per 1,000, the odds of a billion operation calculation landing on the correct answer round down to essentially 0. The fix researchers came up with is called quantum error correction. Instead of trusting a single fragile qubit to hold a piece of information, you spread that information across many physical qubits and monitor the relationships between them so you can catch and correct errors before they spread through the calculation. The dominant method for doing this is called a surface code, and surface codes are brutally expensive. You typically need somewhere between 1,000 and 10,000 physical qubits just to build one reliable logical qubit, and a meaningful. Calculation needs thousands of those logical qubits, not one. Do the multiplication and you land on a number that should stop anyone cold. Millions of physical qubits. As of 2025, the world's most advanced machines had a few thousand qubits at best. IBM's processors were operating in the hundreds. Google's Willow chip, which made global headlines in December 2024 for a historic error correction. Result ran on 105 qubits. We weren't years away from millions of stable working qubits. We were realistically looking at decades. That is the exact wall the University of Chicago team found a door through. And by 2026, that door has become one of the most consequential threads running through the entire quantum computing industry. When you actually sit down and read the paper Professor Liang Zhang and his team published in Nature Physics, what strikes you first isn't the density of the mathematics. It's how elegant the core idea turns out to be, because the solution had technically been sitting in plain view for years. The reason nobody had cracked it wasn't a lack of intelligence or effort. It It was a hardware limitation that the entire field had quietly accepted as basically permanent. The University of Chicago team, working with collaborators from Harvard, Caltech, the University of Arizona, and the neutral atom hardware company Qira Computing, refused to accept that limitation. And that refusal is what makes this paper, years later with hindsight, look like one of the more consequential pieces of physical science published this decade. Let's walk through what the problem actually was, because the details are what separate a genuine breakthrough from the kind of incremental progress that gets dressed up as revolutionary by press departments. In a standard surface code, qubits sit in a flat two-dimensional grid like tiles on a floor, and each qubit can only compare itself to its immediate neighbors. That local-only checking is exactly why you need so many qubits. The redundancy has to be built up brute force, one neighbor relationship at a time. Same neighborhood watch analogy, except now everyone has a radio and a long-range camera covering dozens of properties at once. That's not a 10% improvement. That's a factor of 10 reduction in the foundational resource cost of the entire enterprise. So why wasn't anyone using them? The answer is almost embarrassingly simple. For qLDPC codes to actually function, qubits that sit far apart need to directly interact and exchange information. In conventional quantum hardware, the superconducting chips IBM and Google build and most other qubit platforms, the qubits are physically fixed in place, embedded in solid material, only capable of talking to their nearest neighbors. Asking two qubits on opposite ends of a chip to have a direct conversation was, for years, like asking two people standing on either side of a walled city to whisper to each other. The wall was physics itself. Any attempt to relay information across intermediary qubits introduced so many cascading errors that it wiped out the theoretical efficiency gain entirely. Theorists had found a better route on the map. Engineers simply couldn't build the road to it. This is exactly where the Chicago team's insight changes the picture. Instead of superconducting chips, they proposed building qLDPC architectures on a fundamentally different physical substrate, neutral atoms, trapped and held in position by beams of laser light. And here's the property that makes everything else work. Because these atoms are held by light instead of locked into solid material, they can be physically moved. Precisely controlled lasers can pick up an atom, carry it across the processor to a new position, let it interact with another atom, complete the required quantum operation, and then return it home. The qubit doesn't send information across the chip. The qubit travels to wherever the information needs to go. Distance stops being a barrier the moment you can simply move the participant. The blueprint the team laid out describes an architecture where a qLDPC memory block stores logical qubits. A separate processor unit handles computation, and mobile ancillary qubits shuttle between the two to run the error-checking comparisons that keep everything reliable. The reconfigurable atom arrays handle the mobility. The qLDPC codes handle the efficiency. Put together, it's a physically realistic blueprint for fault-tolerant computation with dramatically lower resource requirements, something that, before this paper, existed only as an appealing but practically unreachable idea. The simulation numbers are what made quantum engineers stop and reread the paper. At a physical qubit error rate around 1 in 1,000, representative of where hardware actually sat at the time, the Chicago architecture needed roughly 10 times fewer physical qubits than the equivalent surface code approach to hit a meaningful fault tolerance threshold. In concrete terms, a computation that would demand millions of physical qubits under the old surface code framework could plausibly be done with fewer than 100,000 physical qubits under this blueprint. That compression isn't a footnote. It's the difference between a machine current engineering could plausibly deliver within this decade and a machine that wouldn't exist until the middle of the century. And this wasn't a purely academic exercise that faded after publication. Qira Computing, one of the leading builders of neutral atom hardware, was a direct research partner from day one, meaning there was already a bridge between the theoretical blueprint and the engineers who actually build these machines. By 2025, follow-up work from the same broader research group, including papers on constant overhead fault-tolerant quantum computation and homological product codes, kept extending the same core idea. And crucially, this wasn't happening in isolation. IBM's own quantum roadmap, which by 2025 and 2026 had shifted its entire architecture around qLDPC-style codes rather than pure surface codes, is built on the same underlying family of ideas the Chicago team helped make physically real. I want to be direct about something, because I think most coverage of quantum computing strips out the part that actually matters to people living ordinary lives. When scientists and tech journalists talk about breakthroughs like this one, the conversation almost always stays abstract. More qubits, lower error rates, better codes. The language stays technical, and the human stakes get buried underneath it. But when you trace the consequences of the University of Chicago blueprint all the way to their endpoints, what you're really looking at is a compression of the timeline on which some of the most urgent problems facing people right now could actually get solved. Let's walk through those consequences one at a time. Start with medicine, because the implications here are the most immediate and the most personal. One of the most computationally brutal problems in biology is simulating molecular interactions at the quantum mechanical level. When a pharmaceutical company develops a new drug, the core challenge is understanding exactly how a candidate molecule binds to a specific protein inside the human body. A process governed by quantum forces so complex and interdependent that no classical computer, including the most powerful supercomputers running today, can accurately simulate it beyond the simplest molecules. That's a huge part of why drug discovery is slow, expensive, and defined by catastrophic failure rates. Industry data has consistently put the average timeline at somewhere around 10 to 15 years and well over $2 billion to take a single new drug from lab discovery to regulatory approval. And most candidates never make it that far at all. A fault-tolerant quantum computer changes that math entirely. Protein folding, enzyme binding, receptor interactions, how a drug molecule crosses the blood-brain barrier, all processes that currently take years of expensive trial and error lab work, could be simulated computationally with true quantum precision before a single physical experiment happens. Multiple serious analyses in the pharmaceutical and computational chemistry world have put the plausible outcome at compressing that 15-year average down to somewhere between 3 and 5 years, while letting researchers screen millions of candidate molecules in pure simulation and only move the highest confidence candidates into the lab. The diseases with no effective treatment today, the ones where the biology is simply too complex for classical machines to model accurately, those are exactly the diseases that stand to be addressed fastest once fault-tolerant quantum computing becomes real. The Chicago Blueprint just moved that arrival meaningfully closer, now to the part that governments and intelligence agencies are already treating as an active emergency, not a future benefit. Nearly every piece of sensitive digital information on Earth right now is protected by encryption that relies on one specific mathematical difficulty. Factoring extremely large numbers into their prime components is essentially impossible for a classical computer once the numbers get big enough. Your banking transactions run on that assumption. Encrypted messaging runs on it. Military and diplomatic communications around the world run on some version of it. A sufficiently powerful quantum computer running an algorithm developed by mathematician Peter Shor back in 1994 could break that encryption entirely. Well, not weaken it, break it, turning what would take a classical computer millions of years into a matter of hours. This is why intelligence agencies have spent years warning about a strategy known as harvest now, decrypt later, where adversaries collect and store encrypted communications today with the explicit plan of decrypting them once quantum computers become capable enough. Classified communications being sent right now, corporate data intercepted over the coming years, all of it potentially readable the moment a fault-tolerant machine comes online, even if the encryption looked unbreakable at the time it was sent. The U.S. National Institute of Standards and Technology finalized its first set of official post-quantum cryptographic standards in August 2024, specifically because governments were already taking this threat seriously before the Chicago paper was even published. Every acceleration in the underlying hardware roadmap makes that migration to quantum-resistant encryption more urgent, not less. And as of 2026, a lot of institutions still haven't started. The geopolitical dimension can't really be separated from the technical story either. China has designated quantum technology a national strategic priority and has been funding research at a scale that rivals the combined investment of the US and Europe, with Chinese teams publishing competitive results across quantum communication, sensing, and computing. Beijing has explicitly framed quantum capability as central to its broader push for technological self-sufficiency. When a breakthrough like the Chicago qLDPC blueprint emerges from an American research institution and then gets picked up by industry players, like IBM restructuring entire multi-year roadmaps around the same family of codes, the clock accelerates for every serious player at once. The engineering path got clearer, the destination got more reachable, and the race to get there first got more consequential than it's ever been, because the real prize isn't prestige. It's the ability to read every encrypted communication an adversary believed was permanently secure, retroactively, across years of stored data. Here's what I think is genuinely important to understand about the moment we're in right now, because the full picture only comes into focus when you stop looking at the Chicago paper in isolation and instead look at everything that's happened across the quantum computing landscape in the roughly 2 years since. The Chicago Blueprint didn't arrive alone. It arrived as part of a cascade of advances that, taken together, tell a fundamentally different story than the one the public has been fed for decades, the one where quantum computing is always 20 years away, Always promising, always just past the horizon. What the evidence actually shows is that the horizon moved, and it moved faster than almost anyone predicted. In December 2024, Google's quantum AI team published results from its Willow processor in Nature that sent a clear signal through the entire research community. Willow, running on just 105 superconducting qubits, demonstrated something researchers had been chasing for years as a theoretical prerequisite for practical fault tolerance: below threshold error correction, meaning that as they scaled up the number of qubits, the logical error rate actually went down instead of up. That sounds like it should be obvious, but it had never been conclusively shown at this scale before, and its absence had been one of the most persistent doubts hanging over whether fault-tolerant quantum computing was achievable in practice rather than just on paper. Willow removed that doubt. Then, in October 2025, Google went a step further, announcing what it called quantum echoes, a verifiable quantum advantage result on Willow, running a specific algorithm roughly 13,000 times faster than the best classical estimate. And unlike some earlier quantum supremacy claims, this one was designed to be independently repeatable on other machines. IBM, coming at the problem from a different direction, spent 2025 and 2026 reorganizing its entire quantum roadmap around qLDPC-style codes, the same family the Chicago team helped make physically real. Its Loon chip, introduced in 2025, added the long-range C couplers needed to connect distant qubits. Its Nighthawk processor, a 120-qubit chip, is targeted at demonstrating verified quantum advantage by the end of 2026, reportedly a full year ahead of IBM's original schedule. Its Kookaburra module, also slated for 2026, is designed to be the company's first quantum error correction-enabled processor storing information in an LDPC-style code. IBM's own published research includes a bivariate bicycle qLDPC code that packs 12 logical qubits into just 144 physical data qubits, a real hardware demonstration of exactly the resource compression the Chicago team modeled theoretically. IBM is targeting its first genuinely fault-tolerant system, called Starling, for construction around 2028 and 2029, aiming for roughly 200 logical qubits running 100 million quantum gates. Google didn't stand still either. In March 2026, Google Quantum AI announced it was adding neutral atom hardware as a second modality alongside its existing superconducting chip program, the exact physical platform the Chicago blueprint depends on for its reconfigurable atom arrays. When the two companies that have defined this field for the past decade both start building toward the same underlying architecture that a university lab first modeled on paper, that's not a coincidence. That's a research community converging on an answer. Meanwhile, other approaches are advancing in parallel. Microsoft unveiled Majorana 1 in February 2025, its first processor built on topological qubits, a fundamentally different bet on hardware-level error protection. IonQ, working with trapped ions, reported in 2025 that a 36-qubit system outperformed classical high-performance computing by about 12% on a medical device simulation with ANSYS, one of the first documented real-world cases of practical quantum advantage, however narrow. And Quera, the Chicago team's original hardware partner, continues building out neutral atom systems specifically designed around the qLDPC approach the 2024 paper laid out. Professor Fred Chong, one of the most respected voices in quantum computing architecture at the University of Chicago, has described where the field stands right now using a phrase I keep coming back to: escape velocity. What he means is that quantum computing has crossed the point where it's fundamentally blocked by unsolved physics. The physics is understood. The theoretical frameworks exist. What remains is engineering. And unlike unsolved physics problems, engineering problems tend to yield to resources, talent, and time in a way that's predictable and, right now, accelerating fast. I want to be honest about where the real gaps still are, because this field has had more than enough hype over the years and doesn't need more from me. The Chicago blueprint was, and largely remains, a theoretical and simulation-based framework rather than a fully built machine running real algorithms at scale. Nobody has yet run a genuinely useful, large-scale computation, breaking real encryption, discovering a real drug, on hardware built this way. IBM's own fault-tolerant target is still 3 years out, in 2028 and 2029. Google's roadmap for a large-scale error-corrected machine still points toward the end of the decade. The gap between today's roughly 100-qubit chips and the million-qubit systems these companies eventually want is still enormous. But here's the honest comparison worth sitting with. The transistor took about 30 years from its 1947 invention to become the foundation of the global technology industry. The theoretical grounding behind quantum error correction today is considerably more mature at this stage than transistor theory was in 1947. and the capital being thrown at the engineering problems, hundreds of billions of dollars across the US, China, and Europe combined, dwarfs anything comparable in transistor history. The University of Chicago team didn't hand humanity a finished quantum computer. What they handed the entire field was a credible, physically grounded shortcut past the exact wall that had blocked progress more than any other single factor. And by 2026, you can watch that shortcut showing up piece by piece in the actual hardware roadmaps of the companies racing to build the real thing. So here's the question worth sitting with. If the physics really is solved and what's left is just engineering, how much sooner does that pull the timeline in? 3 years? 5? 10? And are the institutions handling your data, your money, your communications, actually preparing for that on the same schedule the engineers are? Drop your take in the comments. And if you want to keep watching this race as it plays out in real time, because based on everything happening right now, the next couple of years are going to move faster than almost anything we've seen in the history of technology, stay close. This story is just getting started.